20.3, we're going to talk about the cyclic form of monosaccharides. If you remember back to section 20.1, I drew two examples of monosaccharides, and one of them was a straight chain and the other one was a ring. And so here's where we're going to study those cyclic rings of monosaccharides. And before we do this, though, we have to remember something. We have to review something. You have learned that if you have something like an aldehyde or a ketone, and you react that aldehyde or ketone with an alcohol, and there's some acid present, then you can form an acetal or a hemiacetal. We open up the carbon-oxygen double bond, turn it into two single bonds. We take the carbon chain from the alcohol and add it to one of those oxygens. If we have two alcohols, we could add it to both oxygen. In this example, we only have one alcohol, so we add it once. We call this a hemiacetal. So you did this in something like chapter 17-ish, something like that. Well, the reason that you had to learn all of that was because monosaccharides inside one single monosaccharide molecule, they have both of the necessary components for doing this hemiacetal reaction with themselves. They have the carbon-oxygen double bond, whether it's an aldehyde or a ketone, and they also have OHs like you would find on an alcohol. So they can actually do a hemiacetal reaction internally. Meaning that instead of having an aldehyde and an alcohol reacting together to make a hemiacetal, you have something like, and this is not going to be a monosaccharide, but you have something like this that has the aldehyde and the alcohol, and they react together in the hemiacetal reaction. This is kind of tricky to visualize, like how this would actually work. When you do this sort of internal hemiacetal reaction, the product of the reaction is going to be a ring. It is pretty similar to, our approach is pretty similar to what you took normally. So I'm starting by redrawing my aldehyde or ketone, my aldehyde in this case, and I'm opening up the carbon-oxygen double bond. And I'm going to be taking my alcohol. Oh, I didn't mean to erase that much. I'm going to take my alcohol and I am going to connect it. I'm going to have to just put some of this back. So let's number these carbons so I don't get confused. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I opened up my carbon-oxygen double bond, and I'm just going to connect to one of the oxygens, and my other one is going to get a hydrogen on it. So it looks really, really weird the way that this has been drawn, but we could, if we wanted to, draw this prettier. It's a 6-membered ring. It looks like this. And it's really kind of hard to visualize how all of this happens. Let's put a number on that oxygen so you can see that all together. So what I'm going to attempt to do is show you how this works using like an animation type software for an aldose. And I don't know how well this is going to go, but we're going to give it a shot. Before we go to that, the cyclic form of a monosaccharide has 2 C's. The cyclic form of a monosaccharide is called the Hearth structure. So if somebody asks you to draw that, that's what they're referring to. The Hearth structure is just drawing the monosaccharide in its cyclic form. So let's see if I can illustrate this for you. So what I have here for you is a monosaccharide, and it's got 1, 2, 3, 4, 5, 6 carbons on it. And every carbon has a carbon-oxygen double bond or a single bond to oxygen. And so what we're going to see happen is the formation of an acetal between this guy right here and one of the OHs on this molecule. And there's a lot to choose from. So part of our job is going to be to figure out which one to choose. Oh, I don't know what happened to, I just lost a couple hydrogens. I don't know where they went, but maybe we'll see them come back, maybe not. So what I'm going to do is move this molecule around. This molecule in nature, in real life, instead of being zigzagged out the way that it is right here, it actually likes to curl itself up, which is what I'm trying to draw for you right now, to show you this molecule kind of more curled up. Why it likes that particular conformation, it's just, it's just more stable that way. It's like more cozy. I keep losing my hydrogens on my oxygen, but I'll bring them back. So it starts to curl itself up like this. I'm trying to show it getting curled. And as it curls itself up, or when it curls itself up, this particular oxygen right here, which should have a hydrogen on it, let's put that hydrogen back. I lost a lot of hydrogens in this curling process. So this particular oxygen right here is going to become the alcohol of this aldehyde reaction. Oh, you can't get the atoms too close in this. So what will happen is we are going to take our carbon-oxygen double bond, and I'm going to try to very carefully delete it and then open it up like we would normally do. And we are going to form a new carbon-carbon bond, or carbon-oxygen bond, between the carbon of the alcohol, this guy right here. So we're going to form a bond between this guy and one of these oxygens that we opened up. So I am going to pick this guy right there. When this happens, ooh, that scared me. When this happens, this OH group goes away. It is gone. We've lost a hydrogen. We've got to add a hydrogen down here. And if I can pretty this up a little bit, we are going to see a really nice 6-membered ring. I just lost a carbon when I moved that bond around. There it is back. There's a carbon. And so there it is. There's the cyclic form of this monosaccharide that's just curled itself all up. Notice when it does that curling, it connects between carbon number 5 and the aldehyde. It doesn't connect from one end of the carbon chain to the other. And that's one of the things that we're going to see when we learn how to draw them from scratch.